Hi, here we are going to see about the unit 2 continuation part. So that is h of z is equal to h of s. So here we are, one problem is design a digital Butterworth filter satisfying the constraints. There is 0.707 less than or equal to modulus of h of e to the power of j omega is less than or equal to 1. So for 0 is less than or equal to omega is less than or equal to pi by 2. Modulus h of e power j omega that is less than or equal to 0.2 for 3 pi by 4 less than or equal to omega less than or equal to pi. With t is equal to 1 again using the impulse invariant method. So first we have to write the given data, that is passband attenuation, passband frequency, stopband attenuation and stopband frequency. So step 1 we have to specify the passband and stopband attenuation in decibel. For specifying this, we have to use the formula alpha p is equal to minus 20 log ohm p. For ohm alpha s minus 20 log of ohm s. Step 2 is to choose the t and determine the analog frequencies. So that is omega p is equal to ohm p t, that is pi by 2 radian per second, and omega s is equal to ohm st, that is 3 pi by 4 radian per second. So step 3 is to find the order of the filter, that is n is greater than or equal to log base 10 root of 10 to the power of 0.1 alpha c minus 1 divided by 10 to the power of 0.1 alpha s minus 1 divided by log of base 10 ohm s by ohm p. So when we are substituting the values, we get the n value as 3.92. So rounding the next highest value, we will get n is equal to 4. So step 4 is we have to normalize the transfer function. So there is HA of s is equal to 1 divided by s squared plus 0.76537s plus 1 into s squared plus 1.8477s plus 1. So step 5 is the have to find out the cutoff frequency, that is ohm c. Ohm p by 10 to the power of 0.1 alpha minus 1 the whole power 1 by 2n. So substituting the values of ohm p, we will get the ohm c value in the radians per second. Next we have to find out the step 6, that is transfer function h of s. So h of s is equal to ha of s. The limit will be tends to s by 1.5 s by ohm c formula. So we have to 1.57. So wherever s, we have to substitute s by 1.57 in all the value areas. So then we will receive the answer as h of s is equal to this big answer. Next, we have to find out the step 7, that is using the partial fraction expansion, expand the h of s into h of x. Okay, so that is a by s plus 1.45 plus j 0.6 plus a by s plus 1.45 minus j 0.6 plus b by s plus 0.6 plus 1.45 j plus b star by s plus 0.6 minus 1.45 j. So to find the a and d, we will get a is equal to h of s, that is s equal to 1.45 minus j 0.6. So substitute this value, we will get the answers for a. Then to find the b and b dash, we have to substitute the a is equal to h of s, that is s is equal to minus 0.6 minus j 1.45 s. So when we are substituting the values, we will get the output value. So that is b is equal to minus 0.7253 minus j 0.3 and b star is minus 0.7253 plus j 0.3. Next, we have to substitute the values of a value, b value, a star value, b star value in the h of s equation. So then we will get that we know that t is equal to once again. So for every t we have to substitute once again. We will get h of z is equal to summation k equal to 1 to n ck by 1 minus e to the power of p k z inverse. So while we substituting the values, we will get the h of z value as 1.45 plus 0.1839 is inverse divided by 1.1 minus 0.38 is inverse, like this. Okay. Next problem, challenge 3, that is determine the system function h of z of the lowest order Butterworth digital filter with the following specification, that is 3 decibel ripple in pass band is given and 25 decibel attenuation stop band is given. So for here we have to find out the lowest value. So that is we have to design the Butterworth filter equation and then have to find out the h of z. So first we have to h of s, then we have to find out the a value, b value, and then substitute the values in the h of s, and we have to find out the h of z, that is the summation k equal to 1 to n ck divided by 1 minus e to the power of pk z inverse. So after that we will get the answer. Next thing will be the design the Chebyshev filter of the following specifications using the bilinear transformation. So there is 0.8 is less than or equal to modulus of h of e power j omega less than or equal to 1, 0 less than omega less than or equal to 0.2 pi. Next is 0 h of e power j omega less than or equal to 0.2, that is 0.6 pi less than or equal to omega less than or equal to pi. So the given data are pass band attenuation, stop band attenuation, pass band frequency and stop band frequencies are given. After that first we have to find out the specifying the pass band and stop band attenuation decibel. Next we have to choose the t and determine the analog frequencies. So that is ohm p and ohm s we have to find out. The third step we have to find out the order of the filter. For that we have to use the formula as n is greater than or equal to cos h inverse root of 10 to the power of 0.1 a is alpha z minus 1 by 10 to the power of 0.1 alpha p minus 1 divided by cos h inverse into modulus of ohm s by ohm p. So we will get the output as final answer as 1.207. So rounding this value to next highest value, we will get n is equal to 2. So the step 4 is the poles of the Chebyshev filter can be determined by Sk. So that is equal to a cos phi k plus jb sin phi k is equal, that k is equal to 0, 1, etc. up to n. So where phi is 2k plus n minus 1 into pi by 2n. So we have to calculate the a value, b value, epsilon value and mu value. So epsilon value we have to find out, we have to use the equation as root of 10 to the power of 0.1 alpha p minus 1. So when we are substituting the values, we will get epsilon value. After that substituting this epsilon value in mu formula, we will get the mu value. So mu is equal to epsilon inverse plus root of 1 plus epsilon power minus 2. So we will get the mu value as 3. Next we have to find out the a value. For a finding out the value of a, we will get the equation as ohm p into mu power 1 by n minus mu power minus 1 by n by 2. So substituting the mu value, we will get a value. Likewise for b, ohm p into mu power 1 by n minus mu power plus mu power minus 1 by n by 2. So we will get the value of b. Next, phi is equal to 2k plus n minus 1 by into pi by 2n. So k is equal to 1 comma 2. So we have to substitute the values k equal to 1 and k equal to 2. So that is sk is equal to a cos 5 plus jb sin phi k. So we will get for k equal to 1 we will get s1 value. For k equal to 2 we will get the s2 value. So next step is 5 is we have to find the denominator polynomial of the transfer function. So that is s plus 0.26 minus j 0.53 into s plus 0.26 minus j 0.53. So when we are multiplying this, we will get s square plus 0.530s plus 0.351. So step 6 is the numerator of the transfer function, which will be depends on the value of n. So if n is even, we have to substitute s is equal to 0 in the denominator polynomial and divided by root of 1 plus epsilon square. If it that is we will get the h of s as output value. Next step 7, we have to find the transfer function, that is h of s is equal to numerator by denominator. So after that, step 8, we have to apply the bilinear transformation to obtain the digital filter, that is h of z is equal to h of s limit s is equal to 2 by t into 1 minus z inverse by 1 plus z inverse. So when we are substituting the values, we will get h of z as a output value. Okay. Next is design a Chebyshev filter by using the impulse invariance method. So we have to find the passband, stopband, passband frequency, stopband frequency. So attenuation, we have to mention it in decibel. Find out. Then we have to choose the t value and determine the analog frequencies. Third step, you have to determine the order of the filter. So for order of the filters, we will use this formula and that will find out the values. If the value is in point, we have to round up the value to nearest highest point value.